Preparing students for the maths of 2040, not 1940. Today we're going to be looking at some cool tools, a bit of philosophy and the future, and maybe some discussion and feedback at the end. These are the tools we're going to be looking at: pencil and paper, calculators, spreadsheets, GeoGebra, programming, Mathematica. You'll notice as you go down the list, the tools become more complicated, but they also become more powerful. If you're less familiar with some of the tools near the bottom, hopefully today's talk will inspire you to become more familiar. First of all, pencil and paper. I love paper. I'm in a Facebook group called I Love Paper. I think paper is an incredible resource, and there's nothing that can match it for quickly getting an idea down on paper and getting it out of your head. A couple of weeks ago at the UK Maths Challenge, I noticed one of the sheets was left over, one of the sort of scrap paper sheets one of the lads have been using. This is his sheet, and as you can see, it's got all kinds of different notations and ideas jotted down, and you cannot beat paper for quickly getting an idea out of your head and allowing you to then shift your thinking up a level, because the paper is handling the kind of storage of the data that you're working with. Calculators are 100% accurate all the time, but unfortunately, if the operator puts incorrect information in, it will give a perfectly correct answer to the wrong question. The idea of offloading the mechanics of a calculation to a manual device is not new. The Chinese and Japanese and all the kinds of people have been using this for ages. And in the Victorian era, they were making log tables and other kinds of tables by hand, and they were notoriously inaccurate because it's very difficult for a human being to be infallible. So the difference engine was designed to be able to overcome that problem. Slide rule, again, it's a device for shifting the heavy lifting of a calculation out of your head and onto some other kind of device that will deal with the mechanics, the manipulation, the monkey work, so your brain can deal with the overview of the problem. How do I get this rocket back to Earth, or whatever it is you're dealing with? In the 1940s, during the Second World War, when the mathematicians at Bletchley Park were trying to crack the Enigma codes, they used ever more sophisticated machines that could analyze all the possible combinations that couldn't be true, and they could reduce the number of possibilities from billions to thousands, which then freed up the mathematicians to use their pattern matching skills to quickly ascertain which possibilities were the real codes. So today we're looking at how can we automate doing so that we can elevate thinking. And this is looking at a shift from low-level numeric manipulation, being the definition of maths in school, to high-level conceptual thinking. In my class, whenever we've finished working through a problem on the board and we've done all the algebra and we've kind of worked through the problem, and all we've got left to do is actually finish it off, and we shout Miggins. And the idea of Miggins is that there's two people in an operating theatre. One is the brain surgeon and one is the cleaning lady, and the brain surgeon can do the mopping up after he's done the neurological whatever. He could mop the floor and clean up all the blood afterwards, but that would be a poor use of his time, resources and abilities. He knows how to use a mop and bucket, but that doesn't mean that he should use a mop and bucket. So when we're ready for the monkey work at the end of actually pushing in the numbers, we shout Miggins, and out come the calculators. With my year 5s, a few weeks ago, we were looking at different star patterns, and I was going to show them how to make them in GeoGebra, which is a free piece of software, but we accidentally ended up exploring some polynomials. I showed them how you can do x to the 2, x to the 3, and they went to increasing powers of x, x to the 4, and then of course being little kids they wanted to investigate further, and I think the next one they did x to the 10 and x to the 20 eventually, and they just quite happily mapped these curves, and they could see that the curve was becoming more and more shaped like a bucket, and that the odd number curves were all wiggle shaped, cubic equations and so on. Now, as an adult who understands the computation required to do x to the 20 from -2 to +2, you would never willingly undertake that graph. But because the children didn't know that it was so complex, they quite happily put it in. And as you can see from this graph, as the power that x is raised to gets higher and higher, anything just slightly below 1 tends to 0, anything just slightly above 1 tends to infinity. So very quickly we're getting this steep-sided curve, but all the points pass through 1. That was another thing that they noticed. Of course, the beauty of this is it's not just a static diagram that like you have with pencil and paper. We can create an interactive simulation, so we can look at all possible values. So if we create a slider, we'll give it a variable name n, and then we'll give it a min and a max. So we're going to go from powers of x from 0 to 30, and then that just creates a little slider, and then we can use that slider in any functions from that point on. So we're just putting in y equals x to the n instead of a number, and that's x to the 1 by default. And then as we slide this slider up and down, bucket wiggle, bucket wiggle, bucket wiggle, all the way up to n equals 30, and the curve, the sharpness of the curve in the corners of the bucket is getting sharper and sharper. Hand calculating. Hopefully this is what people in the future will look back on as the maths, or what passed for maths in the 20th century. This was the original question that sparked off my thinking along these lines from the MEP Hungarian translated maths books, which I'm using with year 10. Really nice question. You calculate the area of this prism and then multiply it by the depth. And then a nice little bit at the end there, if some water leaks out of the pool, calculate the distance by which the water level falls. And one of my students, who's quite a smart guy, he worked through this calculation. He's laid it all out very neatly. Great student, but unfortunately, as you've no doubt spotted, when he multiplied 1.7 by 5, he took out the decimal place to do the calculation, but he forgot to put it back in at the end. And so at the bottom, where he's got a plus b plus c equals 25 plus 85 plus 3.4, that 85 should be 8.5. And obviously from that point on, all his calculations are wrong. And so he had to redo all of this calculation to make it correct once he looked at the answers. And that doesn't mean that he's a bad mathematician. He had a full, deep, rich understanding of what the problem was and how to go about solving it. But he just wasn't 100% infallible on the hand calculating side of things. So I said to the students, well, maybe we could take this problem further. Maybe we could create it as a spreadsheet. So here's a spreadsheet version of the same question. The 3 areas are broken down into color-coded, and then the colors are maintained through the whole spreadsheet. So we can easily calculate the 3 areas on the right, and then the total area and the volume. And the nice thing with a spreadsheet is that you can then change the values, and as you go up and down, the values in the volume and the area and all these different things in the model, they change. So that's really nice, and you can have a slider. But I wasn't satisfied with that. I wondered if I could achieve the same thing with GeoGebra. I'd never really tried anything like this before, but on Sunday night I thought I'd have a go, and this was the result. So here we have a model which, as you change the sliders, now the model actually reshapes. So you've now got a visual idea of what's going on as you're changing these numbers. We also thought it would be nice to extend this so that I said, well, what else could we do with this problem? What about the cost of heating this swimming pool? So if we got the specific heat capacity of water and the temperature change that we like, we can calculate the energy to raise the temperature by 3 degrees in this case. And then we looked on the Yorkshire Electricity website to find out the price per kilowatt hour. And then we can work out, we can use this now to model if we wanted to have a size of swimming pool that could be heated for, say, £500 a year, what dimensions of swimming pool could be achieved by that. So we're solving a whole category of problems here. Rather than just solving a one-off problem, we're looking at what's the bigger picture here. And paper and pencil can never compete with that idea. Okay, then we said, well, what's the next step on from that? Because the problem there is that you can only calculate swimming pools that are comprised of 2 rectangles and a single triangle. So then we looked at Python. I'm also teaching programming Python with my year 10s. So we created a prismatic volume calculator, which can take as its inputs any number of rectangles. You can see there's a list of rectangles there at the top. Any number of triangles. You put in the depth and the required temperature change, a couple of constants for the heat capacity of water and the price per kilowatt hour, and then there's 2 or 3 lines where it works through all those triangles and rectangles, adds up all the areas, calculates the volume, the energy and the cost, and then prints them out in a nice format. Okay, so this is a far more generalized problem-solving tool because you can have any number of rectangles, any number of triangles, and you could extend it to curved sections and stuff like that. But the point is, this was actually the quickest of the 3 simulations, the spreadsheet, GeoGebra, and the Python program. This was the quickest one, and it's the most flexible. We've all been in this situation. You're in an airport, there's a list of flight numbers down the side. If you pick the wrong flight number, you end up in the wrong city. So being very aware of your destination is key to getting to the right place. And so we ask the question, where do I want to be? And we have an idea in our head. This is not just about flying a plane. It could be, what do I want to wear tonight? What do I want to eat for tea? Every choice, every decision, every undertaking has a start point and a destination, a desired end appearance. And to get from where you are now to where you want to be, you have to undertake a journey. You have to change something. There's a process that you have to go through to make changes to your world, to make the world look the way you envision it in your head. And in life, you can generalize this process. In ICT, we talk about inputs, outputs, and the processing that is done by the computer, any kind of closed feedback system. What do I have now? What do I want? And how do I move from here to there? In maths, this doesn't really happen. It should happen. It's how it's supposed to happen, but it doesn't happen. The input is list after list after list of similar questions. Jenny's got a bag with 15 different coloured balls in it. Some are red, some are blue. Somebody's picking tickets at the fair. Somebody measured the heights of the children in their class. The children do not have any ownership of these problems. They are not problems that are generated from their experience, from their environment. They sound like children's problems, but they're not these particular children's problems. They're problems that a grown-up has invented to illustrate a mathematical point. When my children were younger, we used to go to the sweet shop with 50 pence, and they had to maximise the amount of sweets that they could get with their money. And if they came out with 5 pence change, you couldn't eat the change, and so in their eyes that was a mathematical failure. So they very quickly became adept at solving this particular problem of how to maximise the amount of money, the amount of sweets, and minimise the amount of money. They cared about the outcome of this problem. If you have no investment in the outcome, if it's just a list of ticks and crosses, if it's nothing to do with your life and you didn't generate the problem, why should you care? There's a level of caring because I'm conscientious and I'm a good worker and I'm trying to please the teacher, but deep down these are non-satisfying ways of tackling maths and the concepts underlying maths. The process section, where we get from an input that we didn't create to an output that we're not interested in, it appears to students that all their teachers are bothered about is the processing, handling quadratic equations by the 50, or adds and takes aways and multiplies, and the mechanical manipulation of givens to find the answer. And where does the answer go? It goes in the bin. These are disposable paper-based answers that nobody cares about. Over and over and over. No wonder children are disenfranchised, disenchanted, and disgusted with maths. And so many grown-ups say, I hated maths at school. I never got maths, because the maths that they were taught was not teaching maths is beautiful, and it's about patterns, and it's about seeing things in a much deeper way. They think it was just lists and lists of questions to answer that go nowhere and come from nowhere. Is this really what we care about? More importantly, is the ability to repeat existing knowledge the skill that our students will most need in 2040? My daughter is 14. In 2040, she will be the same age I am now. Is the maths that she is receiving in school appropriate and preparatory for the maths abilities that she will need to have in 2040? I don't think so. The processing of data, the manipulating of information is not maths. Maths is about seeing a problem from beginning to end. Euclid's 13 books called The Elements collectively expressed everything that we knew about geometry for 2,500 years. And it was taught in schools. It was the second book printed on the Gutenberg press after the Bible. It was fundamental to shaping our understanding of how you go from a start position through an arduous sequence of steps to a desired destination. Euclid begins with a point in space. From a point, he makes 2 points and makes a line. From 3 points, he makes a plane shape, a triangle. And here's his definition of an equilateral triangle formed by the intersections of 2 circles. From this humble beginning, 13 books later, we have the definition of one of the regular Platonic solids, the dodecahedron. You start with a cube. A cube has 12 edges, and along each of these edges we're going to create a pentagon. Using the golden ratio, you find a point on each of the lines, and then you make that go up. You extend it vertically, then you create the pentagon at an angle, and then you replicate that across all 12 edges, and you've now got a dodecahedron. This tool is called Mathematica. It's currently freely available. It's usually hundreds of pounds, but they're running a competition to get children programming in Mathematica at the moment. So sign up, get learning. It's not an easy tool, but it is a massively powerful tool If pen and paper is a trowel and GeoGebra and spreadsheets are JCBs, then this thing is dynamite. Okay, kids often say to me, is this on the syllabus? Will this be in the exam? We have incorrectly taught children that the test is what's important here. In the same way that you don't spend weeks and weeks and weeks learning to drive in order to have a little pink piece of paper and still walk places, you take a driving license test in order to be able to drive places, in order to be able to use the skills that you have learned. And the skills that they are learning in maths are not the skills they will need for driving around. They are not the skills that are out there in the real world. Maths in the real world is manipulated in spreadsheets, in simulators, in programming aspects. Very rarely, if ever, will you need to do any kind of hand calculating like long division, not least because your boss would not trust your fallible human brain to get it right. Do we want to produce problem doers or problem solvers? A problem solver sees the problem from beginning to end. A problem doer is just nose to the grindstone, chunking through the digits, has no concept of why this is being done. And I think in 2040 that job won't exist because a robot will be doing it far faster and more effectively. I often ask my students, if you think you really understand this, how would you explain it to someone who knows nothing about maths? Maybe your grandmother, or your baby sister, or your Auntie Nellie, or a fish. But far harder is, can you explain it to a computer? A human can always fill in the dots. A human will always say, oh, do you mean it's a bit like, and they will bring their own experience and analogies to their understanding of the problem. But a computer cannot do that. A computer can only do exactly what you tell it. It cannot have an original thought. You are designed, humans are the ultimate creative force, the ultimate creative being on this planet, and yet we reduce our creativity to chunking through hand-churned information. It's not what we're best for. What we should be doing is pickling our thinking. I did this work with my year 10s. We wrote some functions to simulate the initial stages that a child goes through when they're learning to do maths. First thing they learn is how to count, and they learn to count by adding ones. And you keep adding ones until you've counted to the number that you want. So we wrote a function called add 1. Then we wrote a function called take 1 away. Then we wrote a function called count on your fingers. And at the bottom you can see we call count on fingers with the numbers 5 and 4. And then in the middle on line 7, where it says define count on fingers, you put a number in your head, that's 5, and you put a number on your fingers, that's 4. And then whilst you've still got any fingers showing, line 10, the number in your head, add 1 to it. At the same time, take away 1 from the number on your fingers. You keep going. Once you've run out of fingers, that's the answer. And you can see in the black box at the bottom, that's 5, 4, 6, 3, 7, 2, 8, 1, and 9. This is actually running in, you see at the bottom it says Raspberry Pi. This is a mock-up Raspberry Pi that I've been using with my Year 8s. They've all installed Raspberry Pi on a virtual machine. And then they've installed Python and they're learning to program the Python machine. The reason there's a pickle jar there is that once you have carefully thought through how to do something and programmed the computer to do it, it will continue to do it forever. It will never get it wrong, it will never get tired, it will never complain. It will tirelessly repeat your thinking every time you ask it to, so you don't have to. So you've got pickled thinking. Programming's really hard though, isn't it? Not really. This is some programming that I do on a Thursday with my Year 5s. We use a program called Scratch, which is freely available. We made a number of games. We did an angle firing game. They basically come up with an idea that they'd like to make a game for, and then I make it on the big screen, and they follow along, and they change the graphics, and they play with stuff, and they adjust the parameters, and they add new features. This was a game for multiplying, doing times tables, I think. So the octopus and the squid are having a race, and the I think that's a squid. It asks questions, and then you type in the answers, and if you get them right, you go forward. If not, he goes forward and you don't. But you're not limited to simplistic type games. With some of the older students, I made a simulator of gravity and vectors, and we were looking at how you use sine and cosine to create the components left and right of the movement of the spaceship. So here it is flying around, and you fire your thrusters, and so there's all kinds of real stuff going on there. High level maths. Okay, the two Adams. The first Adam was made to work in the garden. He was made to change the garden, to process the garden, to cut down weeds, to lay down crops, to harvest food, to cut down wood and make shelters, to do things in the garden so that he would have a picture in his head of what he wanted to make, a start point, which was the garden as it was now, and he would work to transform the garden from its current state into his envisioned end state, his destination. A shepherd oversees the whole process of sheep herding. He looks after the sheep, he feeds the sheep, he takes it to good pasture, he keeps it safe from the enemy, he shears the wool, and he takes the wool to market. He's in charge of the whole process from beginning to end. Industrialization, the Industrial Revolution, broke this aspect of a working man dealing with the process from beginning to end. So instead of a cobbler starting with leather and needles and thread and creating a shoe, now all he does is hammer nails into the soles, and somebody else cuts the leather, and somebody else polishes, and somebody else finishes the job, and he has no pride in his work other than, again, with the student who wants to do what the teacher asks and wants to do it well. There's that kind of pride in your work, but you have no finished product that you have an invested interest in. Adam Smith, the second Adam in this story, he was the instigator of this much narrower, process-focused thinking, which did increase productivity, but what you then find is that your workers become disenfranchised, they don't care about what they're doing, leads to sickness because they're unhappy. And Saab, they realized that this was a problem in their factories, and so they changed their working processes so that people would work in small teams of 10 or so, and they would take a car from a bare frame, and they would put in the engine, they would attach the seats, they would do all the jobs as a team, and they would turn out a finished car. And productivity went up, but their workers' happiness and job satisfaction went up as well. What's the future going to be like? More robots, more automation, less manipulating of data, and more thinking about the problems that lead to needing to manipulate data. Thinking about where do I want to be, and then getting a tool, a computer-based tool, to help me to get there. Because the journey is not the useful part. The journey just wants to be accomplished as fast as possible. You can walk across Australia if you want, but it's far more efficient to drive or fly or take a train. We want to create students who are problem solvers, not automaton, not robots who just churn out answers, churn through data with no concept of why they're doing it. That job's gone. Isn't it great? We have nothing to pay. We have to pay nothing for the barn. Yep, and even the food is free. Facebook and you, if you're not paying for it, you're not the customer. You're the product being sold. If we are going to produce students who are the producers, not the recipients, not the customers, we need to make students who are overseers, who are managing their data, not manipulating their data. When I was a kid, the BBC Micro project and the Spectrum and the Commodore, these home computers created a generation of people who saw the beginnings of programming as a way to manipulate data, as a way to speed up and to understand and to control what was going on around them. Nowadays we have all kinds of great math sites like Khan Academy and Manga High, and there's a new home computer coming out which is aimed specifically at 10, 11, 12-year-old kids. It's called the Raspberry Pi. It costs £15. It's a full-blown computer, and it comes with all the packages that you need to start programming straight away. You can go online with it, you can watch videos with it, you can do all that stuff, but it is equipped to teach kids to program. We've had computers in homes since I was a kid, but nobody uses them to program on because the packages don't encourage that. They encourage you just to press the buttons and use the existing software. In the same way, consoles are non-editable. You can't change the games, you can't do anything to the games. There's no room, there's no scope for investigation and manipulation and playing about. So we need to think up. We need, yes, pencil and paper is great, but we need to get a handle on these more powerful tools and get them into the hands of our children so we can increase their level of generalization, so they're thinking at a much higher level. And currently you can get all of these tools for free, but we have to move fast on Mathematica. Okay. If you need any further information, my web address is bxs.org.uk/MRK, Mr. K.